Hey everyone. We are now in our last section of chapter 6, our section 6.7, which deals with exponential models. This is a section where you will be using your calculator. I will say when it comes to the assessment, you won't need to round it to the nearest tenth, hundredth, or thousandth. You would still get questions like these. You would just keep it in exact form and then move on to the next question. So, but for these examples, I ask you to approximate and estimate and round, which is why you kind of want to use your calculator. So our objectives in this section are the following. We will define exponential growth and decay. We will investigate our continuous growth, where we're involving E, that irrational number that we've spoken about a few lessons back. And then we'll model exponential growth and decay. So you're going to see a lot of application in this section, dealing with things decaying over time and things exponentially increasing and growing. The growing aspect, the most famous example I would say is dealing with bacteria growth. And then from the decay aspect, dealing with like fossils or bones, rocks decaying over time, anything really, honestly, cars decaying over time. But I would say it's more like rocks and dealing with half-lives and stuff. Okay, so definition page. What exactly does it mean to grow exponentially? What does the word double have in common with percent increase? We'll see a lot of doubling throughout this lesson. And so we have three main vocab words. We have percent change, which just refers to a change based on a percent of the original amount. Very self-explanatory. Our next one is exponential growth, which refers to an increase based on a constant multiplicative rate of change over equal increments of time. So that's a percent increase of the original amount over time. And we'll really get to see all of these play out with some general formulas in a moment. And then finally, we have our exponential decay, which refers to a decrease based on a constant multiplicative rate of change over equal increments of time, which is a percent decrease. Decay for decrease of the original amount over time. Right. Our exponential growth, which we already defined over here. Once again, maybe I'll use the same color, blue, refers to the original value from the range, increases by that same percentage over equal increments found in the domain. And then we have linear growth. Think about positive slope, your change in x over change in y. This refers to the original value from the range increases by the same amount overall over equal increments found in the domain. Okay. And then we have just the numerical examples up here. The linear, notice how its increase is a lot slower than the exponential growth. Exponential growth that shoots up real fast. Again, exponential functions shoot up real fast. That's the visual representation, whereas a graph, a linear function, is constant throughout. Right, we have the constant throughout, whereas this is much slower and then boom, much faster. Okay. Now we arrive at our general exponential form, which we've seen before. Our f of x is equal to a b to the x. And the difference between it being a growth versus a decay. Growth is when our b is greater than 0. And then decay, we used, what color did we use for decay? Yellow. Decay is when our b value is between 0 and 1. So think fractions. Okay, and once again, our b from a few lessons back always has to be positive. Our a can be negative, but our b is always positive. Right? A function that represents exponential growth grows by a rate proportional to the amount present. For any real number x and any positive real numbers a and b, such that b does not equal 1, an exponential growth function has our form a times b to the x. Once again, a is that initial starting value of the function, whereas b is that growth factor, or also known as our growth multiplier. So now we finally arrive at our first example for today. We have the population of India was about 1.25 billion in the year 2013, with an annual growth rate of about 1.2%. The situation is represented by the growth function P of t is equal to 1.25 in parentheses 1.012 raised to the t, where t is the number of years since 2013. We want to figure out to the nearest thousandth, so we're going to be utilizing our calculator in a moment, what will the population of India be in 2031? So first off, if we're jumping from 2013 to 2031, how many years has that been? Well, what is 31 minus 13? That is 28, I believe. 18, right? My brain isn't working this morning. Nope, I guess it's half working because that's right. Okay, so now what are we doing? We just want to evaluate what our population is 18 years in. So wherever you see a t, you plug in 18. And then this is your answer. Now we're just going to use our handy dandy calculator to get that approximation to the nearest thousandth. So 1.012 raised to the 18th times 1.25. Did I do that correctly? Yeah. I was like 1.549 people? That doesn't make sense. But it's billion people. So nearest thousandth, 3 decimals over. Which is a significant difference over just 18 years. From 1.25 to 1.54. It's like over 250 million people increased within 18 years. That's insane. Boy, overpopulation. All right, let's move on to example 2. We have in 2006, 80 deer were introduced into a wildlife refugee. By 2012, so we're going from 2006 to 2012. So think in 6 years, it's grown to 180 deer. Whereas in 2006, our initial was 80 deer. Always write down those key facts. And we're given that the population was growing exponentially. So we're going to utilize our exponential function. F of x is equal to a b to the x. Except we're going to be using different notation. We're going to have n of t is equal to a times b to the t. I'm curious if they use those variables over here. No, they used t. Yeah. I was curious what they used over here. But a and b suffices. Okay. And yeah, so now let's put everything together. Again, our initial stands for our a, which is 80. And we have our time there. That was 0 years in, right? So if we were to write this out, n at 0 is equal to 80 times, we don't know our b yet, but again, our time was 0. And then let's do it from 6 years. So now our t is equal to 6. So n of 6, our a stays the same. We don't know our b, but our t is 6. And we know that our n of 6 is the 180 deer. So now we're in a position where we can find our b, right? We have 180 is equal to 80 b to the 6th. And if you're not convinced here that, well, I guess this was just, because we knew what a was from the start, right? Our n of 0 is 80, and b to the 0 is 1, so 80 equals 80. Now let's continue to solve for this b. Zeros cancel out. Half of 18 is 9, half of 8 is 4. So essentially we get b to the 6th is equal to 9 over 4. And then we can go ahead and take the 6th root of both sides. Let me zoom in on this a little bit. Again, b is always positive, so we're going to highlight that it's the positive 6th root of 9 over 4. And we just want to write the exponential function representing this. So now we have all of the information, we just want to put it back into that a times b to the t format. Now that we know what our a and what our b values are. So shrink this and then finally state that our overall result is n of t is equal to 80, in parentheses, the 6th root, right? Forgot the 6 over here. Nine over 4. Computer's glitching out for a second. Sure it's positive. 9 over 4. raised to the t. And we're done. So now let's move on to our second objective, investigating continuous growth. So we're going to be utilizing our E here. And so we have exponential models that use E as the base are called continuous growth or decay models. We see these models in finance, computer science, and a lot of the sciences, so physics, toxicology, and fluid dynamics. And so this general format, a lot of people in finance see it as PERT. Certain textbooks use different values. Sometimes you see it as like f of x is equal to y sub 0 e to the rx. I see it a lot as a is equal to PERT. But we have it here as a of t equals a e to the rt. And again, a is our initial value, r is that continuous growth rate, t is the time. And so we'll really put this into use in the example on this next slide. We have radon 222 decays at a continuous rate of 17.3% per day, which as a decimal is just 0.173. And our units equal days. We have how much will 100 milligrams of radon decay to? So our amount, we don't know what our time is, but we want our amount to drop down to 100 milligrams. And then it says, oh, no, that's incorrect. That 100 milligrams is what it's starting off with, and we want to figure out, okay, what is it gonna trickle down to after 3 days? So our initial, our A, is gonna be that 100 milligrams. That's why it's so important to read the problem, make sure your key is correct. You're labeling everything properly. So our time is gonna be 3 days. Okay. So a to the t is equal to a times e to the rt. And because it's decaying, what's happening here? Your rate is negative, right? Negative sign because it's a decay. If it was a growth, then it would be positive. So we have A after 3 days. Your initial is 100 times E to the negative 0.173 times 3. And now at this point, we're going to use our handy dandy calculator and we will compute it. Okay, so after computing it on your calculator and using your proper use of parentheses, I'm going to round it to the nearest thousandth. 5, 1, 2. So it drops from 100 milligrams down to a little less than 60 milligrams within 3 days. And we're done. Now we're on to our objective 3, which is modeling exponential growth and decay. And so this is going to be dealing with some doubling time problems, but I'll read these paragraphs separately. Maybe we'll use purple here. In real-world applications, we need to model the behavior of a function. In mathematical modeling, we choose a familiar general function with properties that suggest that it will model the real-world phenomenon we wish to analyze. In the case of rapid growth, we may choose the exponential growth function. We may use the exponential growth function in applications involving doubling time, which essentially is the time it takes for a quantity to double. Such phenomena as wildlife populations, financial investments, biological samples, and natural resources may exhibit growth based on doubling time. Okay, very, very common. We see it everywhere. On the other hand, if a quantity is falling rapidly towards zero without ever reaching zero, then we should probably choose the exponential decay model. And that's really linked with calculating half-lives, which we'll practice in a moment. Okay, we use half-life in applications involving radioactive isotopes. Rocks. Okay, so back to the whole doubling time, which we used gray, not a great color. Huh. Not a great color. If the initial size of a population is n sub 0, and the doubling time is a, that's the key here, right? Our doubling time is a, then the size of the population at the time, maybe I'll use a different color here. Doubling time is a. Then we get this general formula. N of t is equal to n sub 0 times 2 to stand for the doubling raised to the t over a. And it's important to know that t, the population at the time, and our a, our doubling time, which you'll get more comfortable with when we look at this concrete example in a moment, they are both measured in the same units, whether it's minutes, hours, days, years, so on. So let's look at this example. And what we can do is, why don't we write that, our general equation, maybe I'll just screenshot it from the previous slide. Put our whole n sub 0 times 2 raised to the t over a. Okay, much better. So we're given that a certain bacteria population doubles every 3 hours. Ooh, that's key. That tells us our A value is 3, right? Our time is affected by every 3 hours. So let's say we're looking at 21 hours. What's going to happen? 21 divided by 3 gives you 7. That means it's going to be doubling 7 separate times over that 21-hour span. And then initially, there are 1,000 bacteria in a colony. So this is going to be our n sub 0. So what do we want to do? Our part A is asking us to find a model for the bacteria population after t hours. So our n of t is just 1,000 times our 2 raised to the t over 3. And we're done. Let's move to part B, which is now asking us to figure out how many bacteria are in the colony after 15 hours. So now our t is 15, which means wherever we see a t in that model that we just created, we are just going to plug in 15 for it. Works out quite nicely because then we're dividing 15 by 3, which is a nice, beautiful whole number. Of 5. And then even furthermore, 2 to the 5th gives you 32. So we're essentially multiplying 1,000 by 32. So technically, you really didn't even need to use a calculator. This is all very computable in your head. We get after 15 hours, 32,000 bacteria are in the colony. And we're done. And then finally, we have part C, which is asking us after how many hours will the bacteria count reach 100,000? And so now we're stating, okay, our n of t is equal to 100,000, and we want to find our t. So we set 100,000 equal to the 1,000 times 2 to the t over 3, and then reverse engineer this right-hand side to get t all alone, to isolate our t value in order to figure out the number of hours. So my first step is I'm going to do the opposite of multiplication, which is division, and divide both sides by 1,000. Let me zoom in on this a bit more. And so that will give us 100 on that left-hand side is equal to 2 to the t over 3. And now I'm going to go ahead and log both sides. Log of 100 is just 2, right? 10 to what power gives you 100? This is just 2. So we end up getting 2 is equal to, and then our power rule, we can bring that t over 3 out in front of the log. So t over 3 times the log of 2 on that right-hand side. And then let's go ahead and divide both sides by log of 2. So now we're looking at t over 3 is equal to 2 divided by log 2. And then last but not least, we're going to multiply both sides by 3 so that we can get t all alone. 3 as a fraction is just 3 over 1, which tells us that our t, in exact terms, 2 times 3 is 6, is just 6 divided by log of 2 hours. But let's put this in numbers that we know and make sense of. So 6 divided by log of 2 will give us 19.93 hours, approximately. right? And so what does that tell us? That tells us a little less than 20 hours, and we will reach that 100,000 in bacteria, which logically makes sense, right? Because 32 or 15 hours in, we're at 32,000. And the way exponential functions work is they continue to shoot up to a crazy number. It's ridiculous how fast bacteria can grow. Or from an investment perspective, it's crazy how fast your money can grow, which is why it's so important to invest in your money very early on. When you're poor and you have no money, that's when you want to start investing. And that concludes this example 4. So now let's move on to another example. We have example 5. A certain breed of rabbit was introduced onto a small island 8 months ago, and the current rabbit population on the island is estimated to be 4,100, doubling every 3 months. So our units here are going to be 3 months. And then let's also write out our general doubling formula. So we can put it in terms of n of t is equal to your initial amount times your 2 raised to the t divided by your a value. And it's saying the current rabbit population is estimated to be 4,100. So 4,100 is the current rabbit population 8 months in. Okay. And then what are we asked? Our part A, what was the initial size of the rabbit population? So using what I wrote down in purple, we want to find our n sub 0. So yeah, any type of question like this, it's so important that you write out your given information properly, which is why it's so important to read the question, like really read the question and understand it. Okay, so now we're just going to plug in and chug. So our t, again, in this circumstance is going to be our 8. So we get 4,100, which is our n of 8, is equal to our n sub 0, which is what we're trying to find. And then times our 2 raised to the 8 divided by our a, which is 3. Right, it doubles every 3 months. And then let's simplify. So that exponent doesn't look too fun. So I'm just going to keep it as 2 raised to the 8 over 3, which tells us that our n sub 0 is just 4,100 divided by 2 to the 8/3, which if we used our handy dandy calculator, we end up getting 645.71. And I'm actually going to make it a whole number because you can't have part of a rabbit, right? 646. rabbits are what we started out with. Approximately. Cool. Let's move on to part B of this problem, where we're asked to estimate the population 1 year after the rabbits were introduced. So just keep in mind, our units are in months. So we need to convert that 1 year into months, which is 12 months. We now know that our initial value is we'll use 646 rabbits. Our A value doesn't change, it doubles every 3 months. And we want our T is going to be that 12 months. And now we can write down the general formula. Again, our N of T is equal to our initial value times our 2 to the T divided by A, since it's doubling. So our N of T is equal to 646 times our 2 to the 12 divided by 3. N of T is equal to 646 times 2 to the 4th. 2 to the 4th is 16. And so I think once we substitute it in the T, we should change this now to 12. Which means about 10,336 rabbits. Also, I'm not one to approximate in the beginning. I'm the one to actually use the exact value and then do that approximation at the end. So if we did use the exact initial value, we actually would have gotten, I want to see how much it varies. Yeah, would have been 10,331. So I'll write that one down too, so you guys could really see it. So again, what we have in red is the more accurate number. But for assessment purposes, you wouldn't really calculate it anyway, because you're not going to have a calculator. So you would just keep it as this and get full credit. All right. So a population that experiences exponential growth increases according to this model. Jumping a little bit away from doubling time now, just dealing with our good old E. So our initial times E to the RT. And then once again, this is just the key of which of the variables stand for, whether it's the initial, the growth rate, the time, or the population. Let's jump into this example 6 using this exponential growth rate. So again, A of t is equal to n of 0 e to the RT. We have our initial bacterium, our n sub 0 is 500. Oops. Let's see. Don't know what happened there. It says a biologist later makes a sample count of bacteria in the culture and finds that the continuous growth rate is 40% per hour. So units equal hours. And then we get our our growth rate is 40%, but we need to put it as a decimal. So this is 0.4. And so now we want to find a function that models this. So we're essentially looking at a of t is equal to 500 times e to the 0.4 t. Which we're now ready to move on to our part B, where we want to figure out what is the estimated count after t hours. So our t is equal, after t hours, after 10 hours, our t is equal to 10 hours. So wherever you see a t in that purple equation we created, we're just plugging in 10. And so you get a of 10 is equal to 500 times e to the 4. And this stands for bacteria. So this is our exact value. But if we wanted to plug it into our calculator to get a rough estimate, we would get a lot of bacteria, 27,299 approximately. And then this finally moves us into part C of this problem, where we're asked after how many hours will the bacteria count reach 80,000? Hence, 80,000 is equal to general formula, which is 500 e to the 0.4 t. And we just want to solve for t. So let's reverse engineer it using our inverse operations. First, divide both sides by 500. 2 zeros cancel out in the numerator and the denominator. We know 10 goes into 880 times. So 5 goes in double that, 160 times. Some quick math. And then now what we can do is we can take the natural log of both sides and then utilize our power rules. So we get ln of 160 is equal to, bring that exponent out in front, natural log of e just shoots to 1, and then 0.4 as a fraction is just 4/10. So that right-hand side, I'll zoom in on this a little bit, is just 4t over 10, which really we can reduce that a bit more. That's just 2t over 5. And then that left-hand side stays the same. Then last but not least, almost there, let's multiply both sides by 5. We get 5 ln of 160 equals 2t, and then divide both sides by 2 to get t all alone. So this tells us that in order for us to hit 80,000 bacteria, we need to have been 5 ln of 160 over 2 hours in. which if we put this into our calculator, it's approximated to be, give me a second, 12.688 hours. And we're done. Which, once again, makes sense, right? Because 10 hours in, we're at 27,000. It's crazy how just another 2.5 hours later, we bump up over 50 grand, over 50,000 of bacteria to hit that 80,000 marker. Okay. So we're towards the end of our section. I believe we have one more example. Yeah, and then we're on to our chapter 7. But this next example is going to involve our knowledge of half-lives. And I just want to make sure that I'm using the proper colors. Half-lives I used as red, so I'll use red here too. Okay. So we have radioactive substances decay by spontaneously emitting radiation. The rate of decay is proportional to the mass of the substance. This is analogous to population growth, except that the mass decreases. So we're not increasing, we're decreasing now. And so a lot of scientists, physicists, primarily express this rate in terms of half-lives, the time it takes for a sample to reduce to half of its original size. And in general, for a radioactive substance, we have our initial mass and our half-life in terms of m sub 0 and h, respectively. It's modeled by our equation m of t is equal to m sub 0 times 2 to the negative t over h, where again, our h and t are in the same units. And then we have our continuous radioactive decay model. So think this is our radioactive decay using 2 as that base, right? Taking a half-life each time versus before it was doubling time. But from a continuous perspective, now we're involving our E, our irrational number E. So if m sub 0 is the initial mass, once again, our h also stands for our half-life. Once again, we are looking at m of t is equal to m sub 0 times e to the negative rt. And in order to solve a problem that does involve your half-lives here, we have that decay rate be represented as our ln of 2 over h. This works. This is our sort of continuous decay rate constant, right? It's not a constant because it changes based off of your h, but you're utilizing this for any decay model problem. Okay. So now we finally arrive at our last example for this section, where we're given polonium has a half-life of 140 days. So we're going to say our H is equal to 140 days. And we have supposed the sample of the substance has a mass of 300 milligrams. So our initial mass is 300 milligrams. we want to find a function. We're utilizing our m of t is equal to m sub 0 times 2. So we're using the decay model, not continuous, so there's no e here. That models the mass remaining after t days. So we're just substituting. Our general formula is just simply m of t. We'll zoom in a little bit. Is equal to 300 times our 2 to the negative t over 140. Now let's move on to our part B. Where we have find a function m of t that models the mass remaining after t days. So now we're using our m of t is equal to m sub 0 e to the negative RT since it's decaying. And our R, right, our decay rate is along the terms of ln of 2 divided by our H. It's decaying, so it's negative here. And we know that our H is once again 140. So negative ln of 2 over 140. And then our m sub 0 is 300. So when we sub this in, once again, I'm going to zoom in a little bit, we get that general formula to be 300 times e to the, you don't want to repeat this negative twice. So if you have the negative here, then maybe what I'll do so I don't confuse you guys, I'll take it out here. So we get negative ln of 2 over 140 times our t. Okay. Almost there. We have a few more. We want to find the mass remaining after 1 year. So you can use either or in this case. You're just plugging in. Remember, our units are in days, so 1 year in days is 365 days. So I think that I am going to use, I'll just use the first one. They're going to be very close to one another. Just one is, the continuous one is slightly more accurate. So when we put this into our calculator, what do we get? We get 49.237 milligrams left. So I wrote both out to show you that you'll get the same exact result, whether you use our first model or the second model. Okay. And then finally, we're at that last part. How long will it take for the sample to decay to a mass of 200 milligrams? So we want our final outcome to be 200. See if we could fit it down here. we get, okay, 200 is equal to, and we want to solve for t, so 300 times 2 to the negative t over 140. And then we want to isolate our t. So actually I might shrink some of this a little bit. All right, that's much better. Just to give us a little bit more space. So let's go ahead, divide both sides by 300. The zeros in both the numerator and the denominator cancel out. So you get 2/3 is equal to 2 raised to the negative t over 140. And then let's go ahead and take the log of both sides. So now what do we have? We have a log of 2/3 is equal to, I'm going to bring that exponent out in front, negative t over 140 times our log of 2. Again, our objective is to get t all by itself. So I'm going to divide both sides by log of 2. So we're left with negative t over 140 is equal to log of 2/3. I need to use a thinner pen. Okay. And then let's multiply both sides by negative 140 so that we can get that positive t. So we get t is equal to negative 140 log of 2/3 all divided by log of 2 hours. Not hours, days. Make sure we have the proper units. Okay, so this is our exact value. If we plug this into our calculator, what do we get our approximate value to be? Let's see. We get about 81.89 days. So what does that tell us? That tells us that after a little less than 82 days, our polonium will drop from 300 milligrams in substance down to 200 milligrams. And so this completes the end of chapter 6. Next time, we will be jumping into our chapter 7 material, focusing on angles. I hope this was helpful. Let me know if you guys have any questions, and I'll see you guys soon.